Google's data centers are legendary. Razor wire, biometric scanners, laser grids, armed guards, 6 full layers standing between the outside world and your data. Now, what if a DeFi protocol took that same obsessive, layered mindset and applied it to protecting your on-chain funds? That's exactly what UltraLiquidity is built to do. And in the next 10 minutes, I'm going to walk you through all 6 layers, one by one, so you can understand not just what protects you, but how and why. Stay to the end, because layer 6 is the one almost nobody in DeFi is talking about. Before we get into the layers, let's set the stage. UltraLiquidity is a yield-focused, decentralized lending and stablecoin protocol, and it runs entirely on-chain on the Internet Computer blockchain. Not on AWS, not on Google Cloud. On-chain. That means every swap, every loan, every stablecoin mint executes inside smart contracts called canisters, running on a public blockchain. No centralized server that can be taken offline. No single company holding your keys. Users sign in with Internet Identity, ICP's native passwordless authentication system. Everything is non-custodial, so right out of the gate, you're already operating in a fundamentally different security environment than a centralized exchange. But non-custodial doesn't automatically mean safe. That's exactly why the 6-layer model matters. Quick question before we dive in. How many DeFi hacks in the last 3 years do you think were caused by smart contract vulnerabilities versus actual key theft? The answer might surprise you. The overwhelming majority were contract bugs, logic errors, overlooked edge cases, integer overflows, reentrancy. The kind of stuff that no amount of hardware security stops. That's the threat model UltraLiquidity is designed around. Keep that in mind as we go through each layer. Layer 1. The Internet Computer's Byzantine fault-tolerant consensus. Every protocol is only as secure as the blockchain it runs on. So let's start at the foundation. The Internet Computer organizes its nodes into groups called subnets. Every canister, every smart contract lives on a subnet, and every node in that subnet independently executes the same computation and has to agree on the result. The consensus mechanism is Byzantine fault-tolerant, which means the subnet stays correct and continues operating as long as fewer than 1/3 of its nodes are faulty or malicious. An attacker would need to simultaneously compromise a supermajority of geographically distributed, independently operated machines just to tamper with a single result. That is your first wall. Let that sink in for a second. On a traditional web app, you compromise one server and you're in. On the Internet Computer, you'd need to corrupt dozens of independent nodes simultaneously across a distributed network. That's not a lock. That's a vault door. Layer 2. Chain key cryptography. This is where the Internet Computer gets genuinely exotic. Most blockchains use simple digital signatures. One key, one signer. The Internet Computer uses a system called chain key cryptography based on threshold signatures. Here's how it works. No single node ever holds a complete signing key. Instead, each node holds only a share of the key. To produce a valid signature, to confirm that a canister's output is authentic, at least 2/3 of the nodes on the subnet must cooperate. If you somehow compromise fewer than 2/3 of nodes, you couldn't forge a single valid signature. Anyone in the world can then verify any result against just one public key. One key to verify everything. That simplicity at the verification layer, combined with distributed trust at the signing layer, is cryptographically elegant, and it's built into every interaction UltraLiquidity's canisters perform. If you're finding this valuable, and we're only at layer 2, do us a quick favor and hit that subscribe button and give this video a like. It genuinely helps us keep making deep dive content on DeFi and the Internet Computer. We've got a lot more coming. ULAD. Now we're talking about security layers. And this is actually the perfect moment to tell you about something UltraLiquidity built specifically for this problem. It's called UL-MASH, the UltraLiquidity Multi-Model Agentic Scanning Harness. Here's the idea. Microsoft recently published research on a security approach called M-Dash, a multi-model agentic system that orchestrates over 100 specialized AI agents across a 5-stage pipeline. The pipeline goes: prepare, ingest code, build a threat model, Scan, auditor agents hunt for logic errors. Reentrancy, integer overflows. Cross-canister trust boundary issues. Validate, debater agents argue whether each finding is actually reachable and exploitable. Dedupe, collapse duplicate findings. And finally, prove, construct a working proof of concept trigger. Nothing gets reported without a working trigger. That adversarial separation between auditors, debaters, and improvers is what drives false positives down to near zero. On Microsoft's own benchmark, our 507 real-world vulnerabilities from the CyberGym public benchmark, their M- system hit 88.45% success, about 5 points ahead of the next best entry. Those are Microsoft's M- results, not UlMash's own measured results. UlMash hasn't been independently benchmarked yet, but UlMash is built to work exactly the same way, and it runs entirely as Rust canisters on the Internet computer. No off-chain scanners, no external CI servers, orchestration and trigger verification on-chain, rescanning on every meaningful code change. That's a fundamentally different commitment to ongoing security than a one-time audit. Want to learn more? Click the link in the description to explore UltraLiquidity, and keep watching, because we still have 4 more layers to cover. Layer 3, Canister Isolation and the WebAssembly Sandbox. Every smart contract on the Internet computer runs as a WebAssembly program inside a strict execution sandbox. Canisters cannot arbitrarily read each other's memory. They cannot reach outside their sandbox to touch the host system. Inter-canister calls follow defined interfaces, and every call boundary is a potential trust check. UltraLiquidity's lending, AMM pool logic, and stablecoin mechanics each live in separate canisters. This means a bug in one module doesn't automatically cascade into every other module. Containment is architectural. Compare that to a monolithic Solidity contract on Ethereum, where a reentrancy attack on one function can drain the entire protocol in a single transaction. Sandboxed isolation is layer 3. Here's a reframe that might help you think about this. Most DeFi protocols are built like open plan offices. One breach and the attacker can walk everywhere. The Internet computer's canister model is more like a building with locked rooms and key-carded doors between every department. Even if someone gets through the front door, they're not automatically everywhere. Layer 4. Over-collateralized lending design. This is a protocol-level security layer, not just a technical one, and it's critically important for anyone using the borrowing side of UltraLiquidity. Borrowing on UltraLiquidity is over-collateralized. You have to put up more value than you borrow. Why does this matter for security? Because it means the protocol is never in a position where a sudden price move can create instant insolvency and cascade into a bank run. The collateral buffer is a designed-in financial shock absorber. The Ultra token, UltraLiquidity's native token, can be used as lending collateral, and every position is visible, on-chain, and verifiable by anyone at any time. There's no hidden leverage, no off-balance sheet exposure, no trusted third-party holding IOUs. The math is on-chain, and the math always has to work. Think about what happened to centralized lenders in 2022. They had off-balance sheet exposure nobody could see until it was too late. On-chain over-collateralized lending is the structural answer to that problem. Transparency is a security feature. Layer 5, on-chain governance via the network nervous system. Who controls the protocol? In DeFi, that's always the most important security question, because a malicious or captured governance mechanism can be just as dangerous as a code exploit. The Internet computer is governed by the network nervous system, the NNS, a fully on-chain DAO. When a governance proposal is approved, it executes automatically. There's no multi-sig committee that can be bribed or coerced into pushing a backdoor upgrade. No foundation with a master key. And UltraLiquidity's smart contract code runs on this chain, subject to that same governance transparency. The Ultra token is used for staking toward governance participation, meaning token holders have a stake in keeping the protocol honest. Layer 5 is aligned incentives enforced by on-chain governance. Here's something most people don't think about. Protocol governance is often more dangerous than smart contract bugs. A bug requires a hacker. A governance attack just requires a bad proposal and voter apathy. That's why on-chain automatic execution of approved proposals matters. It removes the human choke point that's historically been the weak link. Layer 6, UlMash, continuous, agentic, on-chain security scanning. We touched on this during the break, but now let's go deep. Most protocols get audited once, maybe twice, and then they ship. After that, every new line of code is essentially unreviewed until something goes wrong. UlMash changes that model entirely. It's built on the same architectural approach as Microsoft's M-Dash, a 5-stage pipeline with auditor agents that find candidate vulnerabilities, debater agents that challenge every finding, and prover agents that must construct a working exploit trigger before anything is flagged. Zero false positives without proof. And because UlMash runs entirely as Rust canisters on the internet computer, not on external servers, not in a CI pipeline you have to trust, it rescans on every meaningful code change. Security becomes continuous, not episodic. That's the layer that almost no other DeFi protocol has. And it's layer 6. Let's stack all 6 layers together. Layer 1, Byzantine fault-tolerant consensus. An attacker needs to corrupt a supermajority of distributed nodes. Layer 2, chain key threshold signatures. No single node ever holds a complete key. Layer 3, canister sandbox isolation. A bug in one module can't automatically spread to every other. Layer 4, over-collateralized lending. The protocol's financial design absorbs shocks before they become crises. Layer 5, on-chain NNS governance. No hidden master key, no backdoor upgrade path. Layer 6, UlMash continuous agentic scanning. Automated adversarial, on-chain security review that runs every time the code changes, not just at launch. That is the security stack, not marketing copy, architectural reality. Each layer addresses a different attack vector, and together they cover the threat landscape in a way that a single audit or a single mechanism simply cannot. Now, here's a question worth sitting with. If you're earning yield in DeFi, are you thinking about where that yield is being generated and what's actually protecting it? Most people just chase the number. But a yield that evaporates in a hack is worse than no yield at all. The security architecture is our part of the yield story. They're not separate conversations. Now, if you want to understand what you're earning yield on inside UltraLiquidity, we need to talk about UXUSD and UYUSD, 2 yield-bearing stablecoins unlike anything else in DeFi right now. UXUSD's yield is designed to come from strategy-preferred shares, STRC, STRD, STRF, and STRK, plus a preferred share from Strive. That's a yield source backed by traditional financial instruments delivered on-chain. How does that actually work? What are the mechanics? And what's the difference between UXUSD and UYUSD? That's the next video. Hit subscribe so you don't miss it, and drop a comment below. Which of the 6 security layers surprised you the most? I read everyone. See you in the next one.